Hello and welcome back to a fun and exciting lesson in Algebra 2. This is Mr. Bean and today's lesson is on the properties of logarithms. I want you to recall the properties of logarithms. One of the things that we talked about was that if we are taking log base b of the number 1, it will always equal 0, regardless of what the base is. And if you have the base being the same as this thing here called the argument, if these are identical numbers, then it's basically like this whole thing just cancels and you have the number 1. All right, so today we'll be talking about some different properties, but before we get into that, we're going to also talk later on about something called decibels. And so I was thinking, well, decibel levels, how loud something is. Where's some place that's really loud? Sports games, and particular NBA arenas can get pretty loud. And I found video clips of Sullivan, Brust, and Kelly. Okay, well, it's not really video clips of them, but of their kind of like their doppelgangers, their lookalikes at these games. And so I'm going to give you a little bit of taste of one of each of them. So first off, here's the Sullivan lookalike.
If you don't have a toothbrush, there's always plan B. Use your finger.
Cool, man. Come on, man. That's why I never gave fans high fives on the way out.
Brush your teeth.
I never gave fans high fives.
Okay. All right, it doesn't really look that much like Sullivan, but still, that was funny. All right, we'll show you one of Brust and Kelly later. So here we got the properties of logarithms. The first is the product property. Let's make sure you get these written down. You're going to notice that these are actually very similar to properties of exponents, and that is if you are adding two logarithms together and the bases are the same, you can just combine them and make it x times y. Whatever this number is and whatever this number is, you just multiply them together, combine them into one logarithm, or expand them if you're going the other way. Same with subtraction. If you have subtraction and the log bases are the same, it's like doing x divided by y. And now this last one here, the power property, and if I'm going too fast, we may need to pause if you don't have all this written down. This last one, the power property, is kind of cool. You take this exponent, whatever the power is, and it just jumps to the front of a logarithm. And so that's what we get over here with the y value in front. It's kind of like becomes the coefficient. All right, so pause this now if you don't have this all written down, because I'm going to use these in some examples. Number 1, let's expand this. So we have a log base 2. So what I can do is write log base 2 of 3. So that if you think about this, this is 3 times x to the 4th times y. So we'll now say plus log base 2 of x to the 4th plus log base 2 of y. Now we're almost done here because the final step of expanding would be to bring that 4 to the front. So our final answer, if you can squeeze this into your notes, hopefully I left you enough room on there, is plus. Now the 4, the power, jumps to the front, and we'd have log base 2 of x plus log base 2 of y. And there it is expanded. All right, number 2. This base is a 10. Now you don't see it there, but it is a 10. We just don't have it written. So we're going to separate this with, I'm going to give myself a little bit of room. Log, we don't have to write base 10. Log a squared plus log b minus, and now we're subtracting because now we were dividing by c, log c. And then the final answer would be that this 2 here, it's in the exponent, can jump to the front. So it's log a plus log b minus log c. And there's your answer. All right, so moving on to number 3. I want you to pause and try this one on your own. Actually, you know what I'm going to do? I'm going to give you a little bit of some music to listen to. And this will probably be distracting as you're listening to this, and then we'll see if you get the right answer for number 3. Now, if you haven't finished this yet, because I'm going to show you the answer in just a second. Okay, and here's your answer, and be careful here and look carefully because there's probably several of you that missed this, and that is you have to subtract this entire thing. You see this whole denominator here is being subtracted because it's all in the bottom, and so I put parentheses around what would be expanded in the denominator, and then that negative distributes through to both of them. Okay, that's why these are both minus. And then the 2 for the exponent and the 3 for the exponent come down to the front. Okay, so that's what your answer is here. Number 4, now we're going to go the other direction and condense these things. So let's put them together. So we have to double check and make sure that the bases are all the same, because if they're not the same, you cannot combine them. Since these are all log base 3, we can go ahead and combine them. So my first step is going to be that I'm going to rewrite the coefficients here. I'm going to put those up into the exponent. So this will become now log base 3 of x squared minus log base 3 of z to the 6th. And then this addition means we will combine these. So it's going to be log base 3 of, now watch this, I'm going to put some parentheses here, 5 times x squared. That's what's going to be on top of a fraction. And on bottom, we're going to have the z to the 6th, because the subtraction means we'll be dividing by that. Okay, so it's one logarithm that is simplified, condensed into just a single logarithm. That's how you condense these things. Moving on to number 5. Here we all have natural logs, so that's log base e. So that's, we're going to be allowed to combine them. I'm just going to, watch this here, I'm going to take this minus natural log c cubed. I'm going to put the coefficients up into the exponents. And now this is kind of going backwards with like one of the ones we did before. If you look back at number 3, since we're subtracting both the b and we're subtracting the c cubed, this b and the c cubed will end up being in the denominator. Okay, so I'll create my little fraction here. On top I have a squared. On bottom I will have bc cubed. Okay, you could also think of this as you factor out a negative and you'd end up with minus natural log of b plus natural log of c cubed. And so it's all on the bottom. All right. Number 6. Here's one for you to try out on your own. You don't have to pause it yet, because I'm going to now show you Mr. Brust's look-alike at an NBA game. This is kind of crazy. And then after it comes back here, pause the video to make sure you get this one done.
Number 3, Pacers cameraman. His foot has fallen asleep, but he tries to play it cool. No. Check out his feet work. Check out his feet work.
That dude's been drinking, man.
Nice feet work, cameraman.
Okay, I hope you enjoyed that video of Brust there. I love that little dancing move he kind of had there. And this one, hopefully you got this one right. This was kind of tricky because we're dealing all with a bunch of numbers, no variables. Let me show you what I did here. So I took the 2 and distributed. That's one thing. Distribute to both. That's where these 2's come from. And then remember, they come up into the exponent. So on the next step, it's going to be 6 squared. That's why this is 36. And this will become 3 squared. That's where the 9 comes from. Now this 0.5 I wrote as 1/2 instead. And 25 to the 1/2 is the same thing as the square root of 25. So again, 25 to the 1/2 is then becomes 5 because it's the square root. Now, how did I get from this step to this step down here? Well, if you're subtracting the logarithms with same basis, that means we're going to do 36 divided by 9. 36 divided by 9 is 4. And then I just left this one alone. And then log base 4 of 4, that's from the properties at the beginning of our lesson that we were remembering. Log base 4 of 4 is the number 1. So this is your answer here. 1 plus log base 4 of 5. Pretty tough one. I'm sure you really appreciate me leaving you the hard ones for you to try on your own. Okay, good. So now going on to what's called the change of base formula. This formula is kind of cool because it allows us to take a logarithm of some given base. In this case, we'll say it's base c, and you can change it to any base you want. Now, I'm going to call it base b, but it can be anything. And so what we do is, this looks a little bit weird. You'll see how easy this is in just a second. You just say log of something else of a, and then you say log base, that same base, something else of c. These two statements are equivalent. You'll see here in our examples how we use this, because the most convenient bases are to work with base 10 and base e. These are the ones we want to work with. Okay, write this down if you don't have it, because I'm going to move to the next slide here. And here, why do we do base 10 and base e? Because it's so nice on our calculator. It's easy to work with. Calculators have a little button for a logarithm of log base 10 and log base e, so it makes sense to use one of those. See, here's our calculator. Look right here. There's our logarithm button, and there's our natural log button. Okay, so we could use one of those. So here's how this works. If you have log base c of a, you can just type in a calculator log a over log c. Again, these would be numbers here. Or you could do natural log A, natural log C. It's exactly the same thing. So let's do this example. Now, when you're doing these on your assignment, your practice, your mastery checks, make sure you show how you're using the change of base formula. And so that would be, you could do log 7 divide by log 5. You're supposed to write this down, okay? And then you say that that is approximately, and then we type that in the calculator. So let me grab my calculator, type that in real quick. We've got log 7. Make sure I close the parentheses. Divide by log 5. You don't really have to close the parentheses at the end here, but you can. And 1.209, and so we get 1.209 is approximately what this is. Now, just to show you, you don't have to write this part down, but if you were to type in natural log of 7 over natural log of 5, you would get exactly the same answer. It doesn't matter which base you change it to. So if I say natural log 7, close my parentheses, divide by natural log 5, and voila, see, get the same thing. So again, it doesn't matter, but make sure you're showing that. I do want to point out that some of your calculators will have this special option right here where you could actually type in what the base is. Now, if you figure that out, and that's great, but you still have to, on your mastery checks, see, I'm not going to really show this to you because we want you to understand change of base, but if you figure it out, you can use it, but you've got to show on your mastery checks and on your tests and things how to use the change of base formula to get from this one to this one. Okay, so use number 8. Write out how you change the base and what the approximate answer is for number 8. You'll go ahead and pause the video now. And voila, there's your answer, 2.322 approximately. And again, what does that mean? It means that this 2 right here, if you raise it to the 2.322 power, you'd get approximately 5. Same thing with number 7. 5 raised to the 1.209 power would give you 7. All right, done with this. Now let's get into the cool decibel levels. And we are actually done with the main part of the lesson. This is just to help you with some application part that you'll have on the assignment so that you're not quite so confused. Don't worry about stressing about memorizing this equation. If we ever have it on some type of test, we'll give you these equations. We're not going to expect you to memorize this stuff. So the decibel level is the loudness of a function of I. D of I is the decibel level. I is the intensity of the sound. And what's measured in what's called watts per square meter. And then 10 to the negative 12, this represents how loud the intensity is, or what the intensity is of the quietest sound a human can hear. It's really quiet. Okay, that's 10 to the negative 12. Write this stuff down. Pause it now if you need to get it written down for your notes. And then let's go on. All right, here we have a nice little chart. Kind of interesting stuff here. So we have rustling leaves would be about 30 decibels. 0 decibels on a decibel levels would be the softest sound a human ear can hear. Ticking watch, 20 decibels. Okay, this is pretty quiet stuff. Now what's interesting though is that for every 10 decibels you go up, so 10 to 30, that is multiplying by a factor of 10. It's 10 times louder. And so decibel levels, and so then again going from 30 to 40 would be 10 times louder. So that means ticking watch 20 rustling leaves going from 20 to 30, rustling leaves would be 10 times louder than a ticking watch. If we were talking about going to a quiet library though, a ticking watch 20 to a quiet library 40, that's 10 times 10, that would be 10 to the second power, or in other words, 100 times louder. Quiet library and a ticking watch, 100 times louder, 10 squared. So let's see, let's do another one of those. If we have, let's say a normal conversation is about 60. Let's say we're at 60 decibels. We're going up to a lawnmower. That is actually 70, 80, 90, 10 to the third. That is 1,000 times louder. Lawnmower is 1,000 times louder than a normal conversation. Okay, that's how decibels work. And I can also give you an idea for those of you who like to wear headphones. Maybe some of you are wearing them right now. Be careful, because that's really loud. Think about how much louder that is than a normal conversation. 10 to the 5th power. Jeez. Okay. So one of the things that's kind of cool about logarithms, this is something that we use logarithms for, is the decibel levels, also earthquakes, the Richter scale. So I wanted you to take a look at this graph. I'm not going to make you graphing things. Just kind of pay attention to this for a minute. The x maximum is 10. Okay, so around here we're at the number 10. The y max is at 5. I'm going to keep this y max at 5 across. I'm going to show you some other things here. If you'll notice though, this one, I went all the way out to 50. So this one was 10, so that's only right about here or so on this other graph. This one I'm going all the way out to 50, but look at the y value. The y value is barely getting to about the number 2. And if we go to this next graph, now I have an x max of 10,000, way out here at 10,000. And yet, look at the y value. The y value is barely getting to 1, 2, 3, 4. Okay, what logarithms do is it smashes the graph down. It makes it so that it doesn't grow very fast. And so you can have very, very large numbers that you plug into a logarithm, but the y values are small. Okay, that's useful. I know that's a little confusing. That's useful for decibel levels. So we can plug in some numbers here that, well, with Richter scales and with decibel levels, that these numbers can get bigger and bigger and bigger in comparison to each other, but the logarithm, the answer to it, doesn't change that much. Okay, it makes it so that our numbers are smaller and easier to deal with for our y values. All right, so here's our problem. I've got a student here. We'll see if I leave this the same in future lessons or not, but I just chose a student of mine that seems to just be louder when he's there for some reason. It's loud in class. So read through this if you haven't yet. We just got some, in fact, I'll just pause this, let you read through it for just a minute. Okay, and what we're doing now is comparing decibel levels. So the second day was 73 decibels, so we need to know the decibel level on the first day, which means we're going to plug in 4 times 10 to the negative 6. That's multiplication there. So that's going to be 10 log of 10, 4 times 10 to the negative 6, if I can get my pen to work, all over 4 times, not 4, what was it again? I forget myself. No, it's just 10 to the negative 12. All right, there, that's better. And then if we just take a calculator, plug all this stuff in, and we should get, let me grab my calculator and see, and I got 66.02 decibels, so right about 66 decibels. Notice here I plugged in my calculator 4 times 10 to the negative 6 in parentheses. You don't really have to because it knows order of operations here, but I just like to be careful with my fractions. Okay, so I'm going to say this is just about 66 decibels. So we'll probably say approximately 66 decibels. All right, so how many more decibels was day 2? It is 7 more decibel levels. Okay, that was how much louder it was with Elois there. Oh, poor Elois. Okay, look at the next one here. Now we're going to compare the intensities. So how many times louder was it on day 2? In order to do this, we need to figure out what is the intensity on day 2, and then you compare them. So this is pretty tricky. You need a graphing calculator. If you don't have a graphing calculator to do this, really pay attention to how I make this work. So here's what we're actually doing. We're trying to figure out when the intensity, when the decibel level is a 73, what is the intensity? And so we take the equation where here's our I, all over 10 to the negative 12, and we're trying to solve for I, but we haven't learned how to do that. That's actually not till our next lesson, how to solve for a variable that's inside the logarithm, but we can always use a graphing calculator to help us, and this is how we do it. Okay, we grab a calculator, you plug in, let's plug in the right side here, 10 log of I to the negative 12, so that's what I have here, 10 log x, because that's the variable button, 10 raised to the negative 12, and then y2, we're going to plug in a 73. Hit enter. Now when you graph this thing, I'm just going to do a standard window, zoom 6. Chances are that you're not going to see much. Okay, that's because, well, for one thing, one of the y values is 73. So let's at least change the window. Okay, this is important. You're going to have application problems like this, so pay attention here. Let's change the window up to about 100, and then we'll be able to see that 73 line. All right, so come on. There's the 73 line. Okay, well, what about the logarithm one? I don't see where in the world is the logarithm. Well, think about what the intensity, what is our x value, our I value? Okay, I want you to go back and look at this. What was some of our other I values here? 4 times 10 to the negative 6. Think about what that is. That's 1, 2, 3, 4, 5, 6 zeros with a 4 there. It's 0.000004. That's really, really small. So if you were trying to be able to see this, in fact, well, actually, I bet if we just did a calculate, it would find where it is. But if you really, really want to see this, that means we've got to go pretty small. Let's say let's do 1, 2, 3, 4, 4.0000. We'll go 4 ones. That's fine. Except we should say negative 0.1, 2, 3, 4. and we'll see if that's enough. And then 0.1234 and with a positive. Okay, and then let's graph that. Now we're really small. Ooh, look at that. There it is, because we zoomed way in there. The only problem is that doesn't cross yet. So we need to, the maximum value, we need to go out a little bit farther. So how about 1, 2, 3 zeros? See if that's enough. And maybe. There we go, it's crossing. Okay, so now we do our second. Calculate, intersection point. First curve, second curve, enter, and then guess, yeah, give me an answer. And it is 1.9953 e to the negative 5. So this is so close to being the number 2. I'm just going to say it's number 2 e to the negative 5. So what that means is we have that I equals, it's in red, that's okay. I is approximately 2 times 10 to the negative 5. That's just exponential, or not exponential, scientific notation, okay, from the calculator. All right, so now how many times louder is it on day 2? We take day 2 intensity, which is this, 2 times 10 to the negative 5, and we divide it by the intensity from the original, 4 times 10 to the negative 6. 4 times 10 to the negative 6, and that's going to give us, grab our calculator, type that thing in there, 2 times 10 to the negative 5th, divided by 4 times 10 to the 6th, and we get 5 times louder. So our answer is that, and that was incredible that it just worked out to be a nice round number, it was 5 times louder, 5 times louder, just to have one student come back. That's crazy. The decibel levels, when we went from that 7 more decibels means it's 5 times louder. Okay, hey, you made it through. We're going to end this lesson with looking at Mr. Kelly's twin that's at an NBA game. This is great stuff, but your lesson is over. If you want to get started on your practice, you can just watch this for fun. This is Mr. Bean signing off. Rock that mastery check, and I'll see you in the next lesson.